Okay. So we continue. So far we have discussed about EVC motor drive. Then I explained you that how EVC motor can be drive can be implemented. We add it, then motor controller, then inverter for us, and then motor. Okay. Then because this is not motor, so you need to operate it in synchronization with the motor. So for that we have information of Hall sensor. Okay. So from the Hall sensor information we have extracted from the Hall sensor information. We try to find that which are the switches to be selected, and then I explained you the process of selection of the switch. Like this part you see. Like if the three Hall sensors are known to us, HA, HP, and SC, then how to select the switches? Because intention is what? Rotor vacuum unit is temperature limiter. So vacuum, motor phase vacuum temperature limiter. You need to inject a square wave current. To inject a square wave current, you have to select the switches of the inverter, which is going to trigger the, which will ensure that the current will be injected in synchronization with the flat of the vacuum. So for that purpose, we have taken the help of Hall sensor, Hall A, B, and C, and from there we selected the switches, switch 1, 2, 3, 4, 5. Like whenever their turn will come, this particular Hall state, remember that 100, 101, like this one state. Whenever a particular Hall state will come, these switches will be selected. Okay. So this part I explained you, and then further I explained you the case that because in this case it is clear that we use 120 degree mode of operation of the inverter. This is explained to you, and then I also explained to you that what is the meaning of 120 degree mode of operation and what is the meaning of 180 degree mode of operation. All these things I explained to you. Then we also observed that in a particular Hall state, one of the phase, only two phases conduct like this. Here you see. So when you select only the switches, let's say that we select the switch 1 and 6 and 1 in a particular Hall state. So this was also kept high and this was also kept high. Means this is on and this is also on. So the voltage which was appearing was what here? It was appearing only VDC voltage. Yes. And then half voltage will be across this stage and across this stage half voltage. VDC by 2, VDC by 2. So what was happening in this case? That this is the back EMF, what we have seen. And then we were applying a voltage which is like this flat. Okay? Flat voltage was applied. So here you see that this voltage was applied. This voltage was applied here like this. And here it was applying like this. So it was ensuring the current something to appear like this. But the problem here was that then I explained you with the help of this equation. This I explained you how to write this equation. Okay. So here you see that BDC by 2 is the voltage across this phase. Minus back EMF is what the current is flowing here. Minus back EMF equal to LDI by dt means what the drop is going to be there across the coil. So this is there. So you see that this gap is VDC by 2 minus EA will remain fixed. So E is K times speed. Okay, it will remain fixed. But what will happen if this is the situation? You will be able to run the machine at a constant speed. You will not be able to variable speed. So but we want a variable speed in case of electric vehicle. So for that purpose what we have to do? We cannot change back EMF. This is as your requirement. You run your vehicle at a particular speed and it will be fixed. So what we can do? We can work with this VDC. So this VDC can be changed by chopping particular switch, modulating these switches. This I explained. Remember that I consider the case of buck converter. Then supply DC source is there and the switch is there and then strip load is there. So when we were operating the switch on off, then we were able to change the voltage, delta VDC. So same thing is happening here. So by changing here, you are able to make this delta VDC. So here it is delta VDC. So half of the voltage will delta VDC by 2, delta VDC by 2. So accordingly, you can change the voltage which you are applying across a particular phase. So it will be possible for you that you can vary the voltage. So average voltage is going to change, increase or decrease, and so it will be possible that you can is increase or decrease the speed. Hello, last night. Okay, so this is the situation. So we are able to vary the voltage. So that's why we need to modulate these switches. But remember that you cannot modulate anything by anywhere as per your case. Okay, you have to see that what you want. You want to control the voltage or you want to control the current. Our actual requirement is what? See, these things I explained you last class. So our actual requirement is that we have the back EMF like this, and we should be in a position to inject a current which should be synchronized with the back EMF like this, synchronized with the back EMF. This should be this way. And so what is happening? That synchronization is there. This is a reference, but you have to control it. So for that you need a current control, something like this. So it will be being controlled like this. Okay, it will be controlled like this. So this is called current control, where you are ensuring that current is exactly synchronized with the back opposite. Okay, then how to realize this? So basically, when you go into market and you see controllers, different controllers will be there, motor controller. Some controllers will be speed control, okay. Some controllers will be current control, okay. Maybe some will be sensor-based control. This is the situation. Sensor-based control is around giving all information. But you are trying to know the position with the help of the voltage what you are sensing. Terminal voltage is what you are sensing or current what you are sensing. So before going ahead, because now we are going to talk about the control. So to realize this, what we are going to do here, that to control, like maybe like we need to ensure a voltage delta VDC by 2, what we are applying in this way something. Okay, it should be ensured like this. Then only it is possible that you can control. Like see, when this is high, current will rise. Okay, this will rise. When this is low, current will go down. This is high like this. So you will be able to control the current like this. Again here you see this situation, when the voltage is high, the current will rise, low, high, low, high. So you are able in a position to modulate the current. This is the situation. Clear? So two things we are doing here. Current, this is called current control because we are trying to make the current as a control. Okay. So now you will see the different controls will be there. Speed control, current control, and then like this. So please remember that speed and torque, the two main terms are there. When you go for speed control, means you are trying to control the field voltage. Okay. When you are going for the torque control, you are trying to make the current. Okay. This is the speed control is voltage you are going to control. Torque control means you are going to control the phase current. Okay. So just for your information, once again I am drawing this diagram. So we have R, L and this back EMF which is trapezoidal in nature. Okay. So what we are interested in here, this is the neutral point. You remember that we were representing the motor with 3 R L E load. This is R, L and E load. Okay, 3 phases, 3 were connected in parallel. This is R, L and E A. Similarly, there is another one. This is a representation of the motor. Okay. And what you are trying to do? You are trying to inject the current IA. This is IB and this is IC. This is EB, this is EC. I am not putting minus sign. Plus minus you put when you have a AC, DC supply. Okay, plus this it shows that this is the polarity, the convention of polarity in the phase is that representation. Okay, this is the situation at present. So now to know the control, to do the control, what we do, intention is what? We have to inject the current which should be synchronized with the flat top portion of the back EMF. So intention is clear. You see that we have these voltages. These are called, this is C phase. So this voltage is what? VCN. Okay, VCN. This is what? Phase B voltage. So here to here phase B voltage is there. This is VBN. Okay. Similarly here it is VAN. VAN. Okay. So what we will do that we have to realize the current control. So what I am going to do, you please see here. So first thing is that we have to set a current reference. How much current you want to make it? Okay. So let's say that this is okay. Just a moment, huh? We have this battery, onboard battery. Then 3 legs of the inverter are there. So this is at present what I am going to explain you is called current control. Okay. Now phase A, phase B, and this is phase C. So I hope that you are not getting confused anywhere because we go ahead with step by step. Okay. This is EA, this is EB, this is EC, this is neutral point. Okay, this is RL, RL, RL. Okay, these are terminals A, B, and C. So you remember that here I explained you that at a time only 2 phases conduct. At a time only 2 phases conduct. Means let's say that 6 and 1. So how the current is flowing? It goes here, it like this one. It goes to the phase, you see that this phase A, go back, return, and then from here this 6 is on, so it will come like this, and then your path is completed. This is what. So at a time only 2 phases are conducting. Please remember. Okay, only 2 phases are conducting. Here only 2 phases are conducting. So do you understand what is the meaning of only 2 phase conduction? Let's say that here is a DC current. What you are trying to draw from the battery. So this current is flowing. Let's say that this switch was on. This is switch 1. So it goes like this. It goes like this. Like this. It goes like this. Phase A. Phase B. It goes like this. This switch is on. So this is the path of the current what I am showing you. So what is the current here flowing? The current which is flowing here is IA. This is IB. As per the convention we have given a name IA, IB, IC. IC is equal to 0. Okay. So IDC current is going. This is IA. Then it is coming back, and so it is. You see that opposite to IB. So you please see that IA is equal to minus IB is equal to IDC. Same current is there. So if you are going to control this current, if you control this current, then indirectly you will be able to control IA or IB. Okay. IA or IB indirectly you will be controlling. So this is called, if you realize that one, then we call it is as a DC link current control. So this is a quite popular and widely used method for the control of a PLC. It's good controller. Okay, otherwise conventional controller will use only speed control. That portion I will also explain you. So here what we do that we place a current sensor. IDC. Okay, we place a current sensor. Clear? This is the current sensor what we are placing here. So what you will do, you want to control it. So you will have IDC link reference. Okay, this is the reference current. Then you will be comparing it with the current which is flowing in the circuit, IDC. So it will be IDC, you are comparing it. Then you will give it to a controller. So you know about PID controller, you have studied. Okay, so PI controller generally is proportional and integral controller is. So here it is a proportional and integral controller. I will explain you how to design this controller also. PI controller. Then you have a limiter. This is a duty limiter. Duty limiter. So output of this current control is going to be a delta reference. This delta reference is, remember that when you are writing delta will be C by 2. This is same. Okay. So this delta VD, and so you want to limit it because this switch will be either on or off. And we are measuring the voltage with respect to this one. Means this point voltage is VA0 with respect to negative terminal of the battery. This point voltage is, this is B0, means the voltage of this terminal with respect to negative terminal of the battery. And this point voltage is, and this point voltage is BC0, means voltage of the terminal C with respect to negative terminal of the battery. Where is the negative terminal? This one is the negative terminal of the battery. Clear? So when the switch is on, it will be, this point voltage will become the voltage, this one VDC. When the switch is off, what will happen? Please remember, this is an inductive load. When the switch will become off, the body diode of the lower switch will start conduction. Nowhere I have made diode, but you remember that in the previous diagram I made diodes. So if you have an inductive load, inductive current you cannot bring down to zero, because you remember that current through an inductor relax the current, relax the voltage across. It will not make it zero. So if you are turning off this switch, this upper switch you are turning off, then what will happen? Let's say that this is the conduction. Okay, and this is conducting, and now what you want, that we want to turn this off. So what will happen? You see, this will go like this, it will be like this, and because upper switch is off, this is off, because you put this switch off, let's say put this switch off, so where the current will go? So this current will start freewheeling through this body diode. Okay, so when the upper switch is off, body diode of the lower switch will be. When the lower switch is off, body diode of the upper switch will be. This is a way of parking, but we don't worry about these things. Huh? So let me make it as it was. Done? So what will happen? This value will be either switch is on or off. So 1 or 0. So you are going to limit this value to 0 or 1 duty ratio. So now what you are having? You are having a duty reference, delta reference here. Okay. Now we have to generate the PWM pulses. Remember these pulses? We have to generate, then only we can operate it. Because this delta reference is a continuous value. So what we do here, you see, that we try to generate this PWM pulses. So how to generate? You remember that I explained to you that I consider a triangular waveform carrier signal, and then we put a line, and then we compare it. It's the same thing I am going to do here. So here you will be using a carrier signal like this. Okay. And then now the output what you are going to get will be, what the output you are going to get, it will be PWM modulated. This is called delta PWM. Okay. This is a carrier signal. Okay, high frequency carrier signal. High frequency carrier signal. How it operates? You have a signal, you see that, you generate a symmetrical triangular waveform like this. Maximum value is 1. Okay, and let's say that from your control you get some value of delta reference. So what is that delta? Let's say that this is the delta reference what you are getting. This is delta reference you got. So you will compare, you see that negative signal, where is it? That this minus is there and this is plus. So wherever this delta reference will be less than this carrier signal, you will get a high pulse. Okay, so this is that high pulse what you are generating. This is the high pulse what you are generating. Okay, so this is what you are seeing. This is delta PWM, and this is your carrier signal. You can say, right? Clear? Now you see that you have this delta PWM generated. Please go back where we left our Hall sensors. So this is the situation. You see that Hall sensors, switches were selected. If you give like this, what will happen? The switches will be unmodulated. You will not be able to run your vehicle with a variable speed. Okay, so what we have to do now? We have to make the variable speed. So how we can make it? Because we have a zero current control. If you change the torque, the speed will be changed. Okay. Now you see the situation. So what we have got? We got delta PWM here. Remember that from there we have generated. It could be from current control, it could be from voltage control, whatever you want, but you will get a delta PWM. Now what we have decided? We decided that we will modulate only upper switches. Okay? So upper switches means you have to make ANDing. So here you see that we will use 3 AND gates for this switch. Okay? S1, then S3, then S5, okay, and then we will mix this AND with the PWM pulse what you have generated. Clear? So what will happen? Here you have high signal and then here you have a modulating signal, this one. So what will be the output? It will be modulated one. Means wherever both the signals are high, wherever both are high you will get high, and wherever either is low you will get low. This is AND signal. Similarly here you see that this is the second switch. So here you got the switch S1 modulated. Clear? Get signal. Similarly here in this case S3 is modulated. So wherever the turn of S3 will come, and because you are ending with this PWM, you will get a pulse something like this. So it is S3 modulated. Okay. Similarly here S5 will be modulated. Okay. S5 modulated signals is there. And what about S1, S2, S3? They will remain as it is. So S2 will remain, whenever its turn will come, it will remain high. Okay. Whenever its turn will come, it will remain high. This will. So this is S1, this is S2, this one is S3, this is S4, this is S6 signal. Okay. Wherever its turn will come, it will remain high. Done? So let me go ahead, go back. So you see that in this case we have generated these signals. Clear? So now what we have done? We are modulating it. So don't you think that these will also get modulated? So the pulses, gate pulses will be now modulated. Remember that what we have done? Because you are modulating them. This is the situation. So accordingly all these S1, S3, S5, S2, all these will be given to these switches S1, S3 and all to the driver circuitry, and whenever their turn will come, they will start operation. Either they will be modulated, stopped, or it will remain as it is. So I hope it is clear that how we control the VLDC motor which is used in electrical. So it is clear to you? So can I just cancel, because this discussion was something different. So let me make it like this. So now you see that by this way we will be able to make the current control of this. Now you can definitely do the speed control also. So what is the difference between current control and speed control? You see that? Dynamic speed means voltage control I am talking about. So in voltage control layout I am just going to draw. There also it will be the same situation. Okay. For the speed control I am directly making voltage or speed control. Okay. So in speed control what we do, that we have to set a speed reference. Okay. There what we set? Current reference. And how we are getting the current? Please remember here that there is a relation between current and this. You remember that the torque of this motor is 2K IDC. So the moment you set a torque reference, then you get a current reference. IDC reference means your IDC reference is torque reference by 2K, where K is the back EMF constant. This is what it is. This things we have seen before. Okay. So similarly there what we are doing the speed control, means that will come in terms of voltage control. So you set a speed reference. I am now talking about the conventional motor controller which is widely being used in the market at present. So this is speed reference, and then you feedback the speed. Feedback is there. Okay. And then again you use a PI controller. A PI controller. You see strategy is same. PI means proportional integral controller. Can I write here? Proportional integral controller. Okay, done. And then again the duty ratio limiter will be there. Because at the end we are going to realize this or apply the voltage delta VDC by 2 with respect to what? Through what? By changing the duty ratio of the switch. So duty ratio limiter will be there. Duty ratio limiter is that this is 0 and this is 1. So again what will happen? We will get output delta reference, and this will be the same arrangement. There is no change. Again you will be comparing it with a carrier signal. This is what I explained to you. This is 0 and this is 1, and you can say this is a carrier signal, and then here you will be getting the voltage delta PWM. Okay. Same thing. And this delta PWM is what? This will be given to your same circuit. Earlier you was giving delta PWM because of current control. Now you are going to give the delta PWM because of speed control. Clear? This part, selection of the switches and modulation will remain always same. So this module is called switch selection and modulation. This whole arrangement is called switch selection and modulation, or you can say that gate pulse generation. This is the name of this module, where you can write down your algorithm also. Okay. In place of making this AND gate or gate like this. This is to explain you. Okay. So this part is clear, like what we do here. Okay. Now important thing is there. Here we need to sense this speed also. How you sense this speed? This is a challenge or not? This is not a challenge, because in controller there will be some algorithm. In the controller it will be written that you have to sense this particular speed. Okay. So how to sense this? This is what I am going to explain you next. So you remember that we were having. Let me make it new slide. Speed estimation. speed estimation. Speed estimation. So you remember that we were having Hall sensors. Let me draw 6 lines. 1, 2, 3, 4, 5, and this is 6. Okay, this is your 0 degree, this is 60 degree, this is 120 degree, this is 180 degree, 3 pi by 3, 4 pi by 3, 5 pi by 3, and last one is this is 6 pi by 3, means total one cycle 2 pi. Okay, now next we have to draw 3 Hall sensors. 1, 2, and 3 Hall sensors. And how were our Hall sensors? You remember? Like one Hall sensor was getting high from here, you please see that high, and it was remaining high for 180 degree, and then it was becoming low, and then again it was till the end of the cycle. And the second Hall sensor was getting high after 120 degree. This is 60 degree, 120 degree. So this was the situation, and then it was, you see that 120 degree, this is 180 degree. For 180 degree, that Hall sensor was getting, second phase Hall sensor or phase B Hall sensor was getting high, like this one. Third Hall sensor, Hall C, was what? After 120 degree of phase B, this was getting high. This is 2, then here 1, it will come 1, and then it was getting low, and this was the situation. Okay, so this is our Hall A, this is Hall B, and this one is Hall C. Just to avoid your doubt or any confusion here, you please remember that your back EMF is something like this: 120 degree flat, and then it is transition is there, and then it is going like this 120 degree flat, and then transition is there. And likewise for other phases. Okay, this is your back EMF. This is for phase A EMF. Okay, just avoid it. Okay, now what we need to know, that we have to know that what is the speed. So please remember one relationship we know about between the speed and the angular position. Remember that that is what? D theta over dt is equal to omega. That's the angular speed in electrical. If you want mechanical speed, then you have to convert it into mechanical speed. So this is omega. Okay, and so if you are going to integrate, if you want to know the theta position, then you will have to integrate it. Clear? Now, what we do, that we take, let's say that one of the Hall sensor input. So what we are doing, that we are taking Hall A as an input. Okay, then we will be using an edge detection circuit. Okay, edge detection circuit. What it will be doing? It will be making here, suppose that greater than or equal to 0. If HA is greater than or equal to 0, generate high pulse. Okay, so this will be a binary output. This is called zero crossing detection, ZCD. Actually, this is not crossing 0, rather it is becoming high or low only. High or low only. So whenever it is getting rising pulse greater than or equal to 0, it is high. Okay, and for rest of the time, or you can make it more precise, like when it is becoming greater than 0. Okay. Greater than 0 or edge detection, you will get this place. What is going to get? You will be getting this position. Okay, it will remain high, zero crossing detection, greater than 0, and then this is what is a binary number. You will have to convert into a real value, that is with the help of data conversion. So what you are getting? You are getting HAZCD means a value of HA, okay, HA which is a rising one. You are getting it, still it is rising. If you don't use this, no problem. Directly you can, what you do, you can consider the rising edge to this one. Okay. Because in some cases you will find that in some of the algorithms you will find that Hall sensor is appearing something like this. In some of the motors, it will be appearing like this. So you need this algorithm. But for the present case, even though you don't write it, this part, and directly if you try to start from here, so please note that this is rising edge and this is also rising edge. This is rising edge and this is also, next time this is fall. कुछ गड़बड़ क्या किया मैंने? Okay, miss, it's correct. This and this is falling edge. So you have to decide that rising edge to rising edge or falling edge to falling edge. So what you do, like if this is the situation, then you will be doing it. Let's say that your Hall sensor is appearing like this. You will be doing it. Otherwise, you don't need it. So what we do, that we want to integrate. What we want to integrate? Okay, we are going to integrate value of omega. We are going to integrate value of omega which we don't know. Clear? So if you integrate it from rising edge to rising edge, what is this? This is Hall A. Then you get a value of theta. Clear? So by this way, if you do that, you will be able to get to know that information of this angular position from here to here, integrating it. Clear? This is the angular position theta. But please remember that we don't want to find theta. In some algorithms you need theta, but here we don't need theta. So what we are going to integrate? What we are going to integrate? We will have to integrate a constant value. Okay, we will have to integrate a constant value. Why? Please see this value. D theta over dt, this is omega dt, and if omega is equal to 1, if omega is equal to 1, what will be the integration omega dt? It is going to give you some time. So what you will be getting as a time? What you will be getting as a time integration? So what we do, that we set omega is equal to 1 here, we don't make any changes. Okay, we don't make any changes. We just set omega is equal to 1. So this value will be a time value. Clear? So let me make it, erase it and mark here. This is a time value. Clear? So the integration what you are going to get here is what? This is nothing but is a time. This is the integration is something time. And where you will get the time period? This will be the maximum value where if you calculate whole, at the end you will get the time period of this one cycle, one complete cycle. This is a time period. So you need to hold this position. So let us consider that you integrate from here and then you reach to this final value. So again when you will get the rising edge, it will reset and again it will go like this. Again it will go down. So this will be the movement. This is time scale, what we are putting here, time, and we are integrating over time. So this maximum value is your time period. So what you need to do, you will have to hold this position. Hold this position. Till what? Till the next rising edge. Where the next rising edge is going, let me draw here. Just to avoid your confusion. So this is our Hall sensor. This is Hall A. This is half. This is each rising edge. Rising edge to rising edge you are integrating. So multiple cases I have considered. Okay. So you have to hold this position till the next calculation is done. So what we do, that we use here a sample and hold arrangement. These block sets are there. And so where it will be, up till what it has to hold? It will hold up from rising edge to rising edge. So take the same Hall sensor signal and give it here to get that same Hall rising edge. So here what the value you will be getting, that is your time period. Clear? Time period. And so what you have done, you have folded this to the next cycle by using the sample and hold. So this will be folded. Okay. So from the previous also, so this is what the line you are getting. This is your time period. And if there is a change in the speed, this T will change. So this you will get a different value. So you remember that what is T? Now T is known to you. So what is the angular speed? You remember that omega is equal to 2 pi by T. This is there. So you have to take the reversal of this one. Reversal of this one will be there. But remember that if T is 0, what will happen? It is problem is divided by 0. That is not going to work. So what you will do, that here you will set some minimum value of T. Some minimum value of T, and maximum, no problem. Divided by very large value, there is no problem, your speed will be 0. Okay. So before going ahead, here you have to limit it to some value. Like sir has also explained in so many cases that you have to set some minimum value. So this is the T final will be there, and then you will be multiplying, you will be taking the reciprocal of this one, 1 by x means 1 by t, and then you will be multiplying it with 2 pi, so you will be getting the value of omega. Okay, this is what the omega is there. So minimum value you can set, like let's say that it is 0. Let's say that 1 microsecond we consider for an example, minimum value of this thing, and maximum could be anything. So max value you can write INF or whatever you want. INF also you can write here. INF. Okay. This you can limit it. So finally you will be getting omega. But please remember that this omega is an electrical angle. Okay. So you have to convert it into mechanical speed. So what will be the mechanical speed? Number of pole pair times now. Electrical speed divided by mechanical speed. This is electrical speed. So electrical speed by number of pole pairs. Suppose that your machine is 4 pole pairs. So 4 pole machine. So what is the number of pole pairs? Okay. If it is 16 pole pair, what is the poles? Then what is the pole pair? It is 8. So by this way you can measure the mechanical speed. So this is one of the we have done. If you want to make like more reliable, you can get done with all other phases also. Okay, and you can update your speed after each 120 degree. Like here it is calculation is done. Previously you use this calculation for hall C. Then after again 120 degree you can update it like this one. So this is your algorithm, but I'm just explaining you with one of the phase. So mechanical speed is known to you. Now this mechanical speed is calculated. Okay. So here I can write here that speed estimation, and what the input are, HA or B or C. So by this way you can realize your speed control. So here two purposes, speed estimation is done. So from the Hall sensor you get two information. One, Hall states, and the second, speed. These two things. So this is about the how you are going to control your machine. Okay, I think I have some time, sir. Anyone is having any doubt, please ask me. I will share your video also, don't worry. So if you have any doubt, you please. Now, the problem is what? Now the problem is that we don't know what value we should put here. PI controller. Okay? Or what value we should put here in current controller. Okay? So please remember that suppose that you want to realize a control, in which X is the reference. Okay, and you are comparing a feedback S, then you are going to get an error. Okay, this is not the back EMF, so that's why I am writing ER. Okay, and then you are going to give it into your PI controller, PI or PID controller, whatever you want to give. So this error signal is what? This error signal as a function of time is X reference minus X. This is the value. Okay, you can write this is in time, so you can write in time. This is in time. Done. So you remember that what is how we write that. Let's say that this output is Y, and here what you are doing, you are giving this error signal into this PID controller ERT, and so you are getting an output YT. So YT is given by KP into ERT plus integral constant KI ERT dt plus KD DERT over dt. This is what it is. A PID controller. So you don't know that what these values are. KP, this is KI and KD. So you need to find out how to do it. But please remember, for an example, just to represent you, if let's say that our response of a system is something like this. Something like this. This is a response. Let's say that this is YT, for an example. Okay, so in this case, what this KP do? So this is the final value, let's say. So this KP will move this gain. KP basically changes the gain. So it will move this curve up or down. Okay, up or down. It will increase or decrease the gain, just to reduce the error. But it has some limitation. It cannot go beyond it. So, okay, but we cannot go beyond it. Suppose that, let us consider a case of the situation, such a situation that this is your reference and you are reaching to this value in a steady state. I am talking about this line. This line. Okay? This line. But what is your reference? You have to reach to this final value. So you cannot do it. So what we do, that we integrate it. The error is to be integrated. This is the actual value. If you count the error, it will come here. It will come something like this, and this is the error signal. This is your error. Okay, error what we are saying. So this is the situation. So you remember that if you integrate a constant, what you get? If you integrate a constant, what you get? A ramp. Okay. So the moment you are going to put this integral, then it will make it a ramp. Clear? That this portion of the signal will become a ramp. This is flat, this is going to make a ramp. So what is possible now, you are able to reach to this, cross this position. So your control action will take place and finally you will be able to reach to your final estimate reference. So this is what the integral is do. And what this KD do? That KD basically it is what? It is the slope what it is getting affected. So basically if you do this one, this portion responsibility is that it can make your response faster. Okay, or it can make your response slower. So basically this part, this and this is done by dET over dt. Okay, so this is what the role of a PID controller is. You got it? So next class we will learn especially modeling of the motor. That's another class also. Modeling of the motor and then how to calculate this PID. Then I will run the simulation and show you how this is solved. Anyone is having any doubt? So you got to know that. So we will not be using D. We will be using only KP and KI.